Now we're going to do a goodness of fit test, a chi-square test for this. Uh, let's see, we observed the values 0, 1, 2, 3, and 4 these many times. This is what we expected. And so for a binomial random variable, we would have expected to see these values. So we want to check, is a binomial distribution a good fit for this random phenomenon, whatever it is. I know we haven't talked about what binomial variables are, but we don't really need to know what a binomial variable is. So suffice it to say, if x was a binomial, we would have, after observing this phenomenon this many times, we would have gotten 1.6 zeros, 25.2 ones, 151 twos, 402.6 threes, 402.6 fours on average, or in expectation, right? You know, we're never going to get exactly 1 point. If this is we're rolling the die, whatever it is, you're never going to get the number 0 to come up 1.6 times. That doesn't make any sense. With expected frequencies, that's an on average. It's like a long-term average, so it's a theoretical average for this, right? And that's okay. I mean, for calculating whether this follows the model, it's okay for us to have little decimal places in there. So here's how we do it. We're going to click this little button, open this in StatCrunch. All right, so we've got of our observed and expected. So under the stat menu, go down to goodness of fit, chi-square test. Our observed is observed, and our expected is expected. Well labeled. And we just click compute. So what do we have here? We've got, so for what we've observed versus what we would expected, we got a chi-square value of 14.232. The chi-square is the test statistic that we calculate for this type of a problem. So if the chi-square, loosely speaking, what we observed is vastly different from what we expected, the chi-square test statistic will be bigger and bigger and bigger. If what we observed is very close to what we expected, the chi-square value was going to be close to 0. So if a chi-square value is really, really big, we're going to get a very small p-value, and we would reject the null hypothesis that this is a good fit for our model. Like this distribution matches what we got in practice. So anyway, let's copy the chi-square value in here and let's walk through the rest of the problem. How many degrees of freedom? It tells it to us right here. There's 4 degrees of freedom. df is degrees of freedom, 4 degrees of freedom. In this case, it's one less than the number of we call them treatments or levels for this single factor, but don't worry too much about that. It's given to you right here in the output table. df is degrees of freedom, 4 degrees of freedom. The critical value for chi-square. To answer that, let's go up to the stat menu, calculators, pull up a chi-square calculator. For a chi-square calculator with degrees of freedom of 4, we want to find what's the critical value that's going to leave only 0.05 in the tail. 0.05, put it down here, compute. Remember, we're doing this inverse. And here's, I want the upper tail, not the lower tail. So let's do that again, 0.05, click compute. Here we go. So the critical value is 9.48. 7, so it's 9.488. 9.488. So if our test statistic is in that red region, right, if it's bigger than 9.488, then we would reject the null hypothesis that the random variable is binomial. We would reject this expected distribution. We would say, nope, we are not matching it. This is probably not what our variable is doing. So should the null hypothesis be rejected? Yes, because chi-square is greater than the critical value.